This video is all about radicals, so square roots and nth roots. Uh, Basically, the goal for now, anyway, is when we're looking at radicals, we want to be able, or problems that involve radicals, we want to simplify them. We want to put them in what's called simplest radical form. That seems like a real straightforward thing, but there's a lot that goes into it, and we'll talk about that. Then how to manipulate a few different kind of problem types and sort of explain what the overall objective tends to be. So, a quick review of radicals, and the most common radical is a radical of index 2, also just called a square root. We have this radical sign, and usually there's a number right here. Or not really usually, I guess most commonly you don't see a number there, and that's because we assume if there isn't a number there that it's a square root, that there's an index of 2. So if you see, for example, right here, there is no index listed there, that means it's 2. It's just assumed. And so we call these square roots. And what is a square root? Well, a square root, the elements of this thing, right, whatever goes underneath this radical symbol is called a radicand. And the radicand is like a product where something was multiplied by itself a number of times that corresponds to the index in order to be this. And so how you would evaluate a radical is to determine what that thing was that had to be multiplied by itself the index number of times to be what the radicand is. So for example, right, the square root of 4, something had to be multiplied by itself 2 times to be 4. That thing is 2. Okay. Same deal here, right? This 36. What had to be multiplied by itself 2 times in order to be 36? 6. Okay. If you just kind of naturally know what to do with square roots, you're right. That's it. It's really like something that at this point here, and when we're starting trigonometry and pre-calculus, it should almost be second nature to deal with square roots. Where things tend to get a little more tricky is when we deal with nth roots. So radicals of degree with an index different than 2. So for example, 3 here, right? I purposely explained the situation with just square roots in the way I did on the previous slide, because nth roots, it applies that definition, that way of explaining it applies for any radical of any index. So 8, this radicand is a product that represents something that needed to be multiplied by itself the index number of times. So 3 times. Something had to be multiplied by itself 3 times. Well, that thing is 2. Okay. We also have a strategy here where if we can find something that had to be multiplied by itself 3 times and the third root, well, that is the answer. It's 2, right? If we can match that index and that exponent, then we can just pull that thing out of the radicand, or out from underneath the radical there. And so we'll see that as we go. But another property of radicals is this: if we had the nth root of xy, that is the same thing as the nth root of x times the nth root of y, as long as x and y are real numbers. Okay, so this is really useful because it'll allow us to separate things that can simplify really easily from things that require a little bit more work. So for example, in this problem here, the third root of x to the 5th times 27. Well, 27 is 3 cubed. So right away we can pull, that 3 can come right out. Then we have to manipulate this one a little bit more. And what you can do here with this cubed root of x to the 5th is say, oh, that's the same thing as a cube root of x cubed times the cube root of x squared. Remember, exponents, right? If I multiply x cubed times x squared, I'll have x to the 5th. So using this property, right, we can take these apart, and then we have then x can come out, right, because these match, and we still have left in the radicand, the third root, we have this x squared. Okay, so that is kind of just how you deal with nth roots, and it's a little bit more complicated than square roots, but it doesn't need to be a big significant challenge. Okay, so again, here's that property of radicals, right? We just said this one, that's as long as a and b are real numbers, and then also I think it's the exact same thing is that this other property of radicals is also the case, and will be very useful if we're dealing with fractions. So for example, I don't know, if we had the square root of 4/3, well, this can be simplified to 2 over the square root of 3, because I could have written that as the square root of 4 divided by the square root of 3. The square root of 4 is 2. Square root of 3, we don't really know, well, you probably do know, but in this video we haven't covered yet what to do with that square root of 3 in the denominator. Usually we're asked to leave an answer in simplest radical form. And simplest radical form consists of a couple things. First of all, you can't have a rational number within a radical. So in this example here, we have a rational number within a radical. We can't have that. So what we need to have instead is something like the square root of 6 divided by the square root of 5. But then there's even more to it, right? We have to clean something up, because we also can't have a radical in the denominator. So how do we deal with that? So this is another example where the radical is in the denominator. And then the last thing we can't have is a radicand with the power of the index. And we have that here with the square root of 4x, because this can be written as the square root of 2 squared x. Well, here's a radicand. This 2 is part of the radicand, and it has a power that's the same as the index of the 2. You know, there's a 2 right there. So that 2 would need to come out before it would be be in what we call simplest radical form. Okay, so these would be the simplest radical form versions of those radical expressions. So let's deal with with dealing with nth roots and putting something in simplest radical form. So we know that if this exponent is greater than or equal to this index, it can be pulled, or some part of that variable in the radicand can be pulled out. So x cubed cannot be pulled out here at all. There's no x's that can come out. There are enough y's, right? There's 5 of them, and we only need 4 in order to be able to pull out a y. So if we pull a y out, we'll still have 1 left over inside. And this 11, clearly we can pull 2 out, and we'd have 3 left over, right? So if we rewrite this, this could be the 4th root of x cubed times y to the 4th times y, that would be y to the 5th, times z to the 4th times z to the 4th times z to the 3rd. 4 plus 4 plus 3 is 11. So I can take out then, this whole y can come out, both of these z's can come out. So I'd have y times z squared, and then that's all times the 4th root of whatever could not come out, which was x cubed y z cubed. One of our requirements for simplest radical form was that we can't have radicals in the denominator. We would need to do something called rationalizing such an expression. So here's 2 examples where we need to rationalize the denominator in order to get these into simplest radical form. So the way you would do that is to just multiply the expression by 1, but we're going to do it in a very specific way because we want to get rid of that the radical in the denominator. So if we just multiply this by the square root of 2 divided by the square root of 2, well, square root of 2 times the square root of 2 is just 2. So the denominator of this becomes 2. There are no more radicals, and the numerator stays as 3 times the square root of 2, and there's nothing further that we can do to simplify this. On the next problem here, there are a few things we can do. One way to do it would just be go right ahead and multiply by the square root of 10 over the square root of 10, just like we would have done if we follow that same procedure as in the problem above. And this would give us 4 times the square root of 60 times 10, right? But there's some simplification that can be done here, because 4 and well, there's a few things we can do here. We're not in simplest radical form anymore, because we can say that that's 4 times the square root of 2 squared times 15, because 4 times 15 is 60, so we actually square root of 60 is not simplest radical form. And then we have 10 here. We could take the 8 out, we could take that 2 out, so 4 times the 2 is 8, times the square root of 15 divided by 10, and then of course 8/10 reduces to 4/5, so this would actually be 4 times the square root of 15 divided by 5. Okay, now that's one way to think of it. Another way, and this kind of goes back to our rational expressions thing, is couldn't I also write this as 4 times the square root of 2 times the square root of 3 divided by what am I thinking? Square root of 2 times the square root of 5. Well, hey, look, I can get rid of these square roots of 2 right there, and that's going to save me some simplification as we go. So if I then took this and multiplied it by the square root of 5 divided by the square root of 5, because that's not what's in the denominator, I would have my answer directly as 4 times the square root of 15 divided by 5. So same answer, different way of approaching it. It just goes to show that if you can simplify something before going ahead and doing the rationalization, it can be helpful. So if we want to rationalize an nth root, something that has an nth root in the denominator, it's not quite the same as when we rationalize something with a square root. The thing we have to multiply by is whatever is just enough to get rid of that nth root. So in this example here, if we look at this, if we took this and applied the previous thinking, where square roots to this is what would happen. We'd have 3 times the cube root of 2, and if we multiply this by the cube root of 2 over the cube root of 2, we're not rationalizing this because the denominator is going to be the cube root of 4 divided by 3 times the cube root of 2 divided by the cube root of 4. But that radical is still there, right? So instead, I would have had to multiply. Basically, I want this 2 to be 2 cubed, so I have to multiply it by 2 squared in order for it to be this 2 before we made it a 2 was the cube root of 2 cubed. And because those were the same, we just made it the 2. So you have to multiply by just enough in order to get it out, in order to be able to pull whatever's under the radical out. Okay, so for example, right, what would I have to multiply a divided by the cube root of b squared by in order to rationalize this? The answer is you'd have to multiply it by the cube root of b divided by the cube root of b divided by the cube root of b, because this would then result in the cube root of b cubed, and then you'd have a times the cube root of b. Obviously, because these match, it comes out as b. This would be a times the cube root of b all over b. We also have to rationalize when we have not such simple things in the denominator. And there's a specific thing we use for this, and it's called the conjugate. So if we have square root of 2 minus the square root of 7, the conjugate is called the square root of 2 plus the square root of 7. And you might notice that this is basically a difference of squares situation here. Imagine if we squared the square root of 2 and squared the square root of 7. Well, now there would be no radicals, huh? So if we had, what I'm saying is if we had x plus y times x minus y, these things are called conjugates of each other, and what happens is when you multiply them out, you end up canceling out these middle terms, and you're left with just the squared parts, just the difference of squares. Okay, so for these, if you were to multiply these out, you would get the square root of 2 times the square root of 2, which is 2. Sorry, well, the square root of 4, right? Let's write that. Square root of 4 minus the square root of 14 plus the square root of 14 minus the square root of 49. Okay, well, hey, look, these go away, and all we're left with after we put the square root of 4 and the square root of 49 in the simplest radical form is 2 minus 7. So that 2 minus 7 becomes 5. This 6 still distributes into the square root of 2 and the square root of 7. So you still have that, and that's ugly, but this answer here is rationalized. It's in the simplest radical form. Okay, now this one is very similar, right? We have to multiply this by the conjugate, and we can't just multiply by the square root of 5 minus the square root of 7. It has to be multiplied by 2 times the square root of 5 minus 3 times the square root of 7. We're multiplying it by 1, right? We can multiply anything by 1 and it doesn't change. We're just doing a really strange looking 1. Then when you FOIL this out, when you multiply this out, okay, you would have 4 times the square root of 25 minus 6 times the square root of 35 plus 6 times the square root of 35 plus 9 times the square root of 49. So we would have, this would be 4 times 5, which is 20, minus 9 times 7, which is 63. So you would have negative 43 in the denominator here. Now, these steps, right? We know that when we're doing these conjugate things, they're always going to cancel out. So you don't have to write that as you're going through the process of solving these, because you know by multiplying by the conjugate, you're eliminating those two middle terms. And same thing here. This is just using the advanced distributive property in order to multiply these two binomials together. So you would multiply these two together, you'd have 12 times the square root of 4, which is 2, we know, okay? But then you would have middle terms, right? You're going to have 4 times, this is going to be plus 8 times the square root of 6, plus this would be 3 times the square root of 6, and this would be, what would that be? That'd be 2 times the square root of 9. So this would be 12 times 2, or 24, plus is a total of 11 times the square root of 6, and then 2 times the square root of 3 is 6. So this would be 30 plus 11 times the square root of 6.